In this video, we're going to talk about free energy, which is a decision-making tool that we can use for determining if a reaction or change is going to be spontaneous or not under certain conditions. Going back to the second law of thermodynamics, remember that for any spontaneous process, the entropy change of the universe has to be positive, which means that the sum of the entropy change for the system and the entropy change for the surroundings has to be positive. There are four possible system enthalpy and entropy cases that could exist. One of them is if the reaction is exothermic, delta H is less than 0, and also there's a decrease in entropy. Another possibility is that the reaction is exothermic, but there's an increase in entropy. The third case would be if the reaction is endothermic and there's a decrease in entropy. And then the last case is that if the reaction is endothermic, but there's an increase in entropy. Now, you can probably common sense your way through a couple of these things, but let's take a little bit more rigorous approach. Let's look at each case individually. Let's look at, first of all, the reaction being exothermic, delta H is less than 0, and delta S is greater than 0. Keeping in mind that in order for this reaction to be spontaneous, the sum of the system's entropy change and the surroundings entropy change added together has to be greater than 0. If the entropy change for a system is negative, that's an exothermic reaction. That means energy flowed out of the system into the surroundings. So that means that the enthalpy change of the surroundings had to have increased, which makes the energy more dispersed in the surroundings, which means the entropy change has increased. Another way of thinking about this is that the entropy change for the surroundings in this case is going to be equal to Q over T, but Q is going to be a positive number in this case because energy flowed from the system into the surroundings. So that means the entropy change for the system, which was already positive, and the entropy change for the surroundings we have now seen must also be positive. If they're both positive, then their sum has to be positive. So this represents a case where the reaction was always going to be spontaneous. Delta H is less than 0, delta S is greater than 0. Both conditions, decrease in enthalpy, increase in entropy, favor spontaneity, so this is always going to be a spontaneous reaction. Let's look at the next case. Delta H is less than 0, and delta S is also less than 0. Okay, so we've already seen that if delta H for the system is less than 0, that means delta H for the surroundings is greater than 0. That means energy is more dispersed in the surroundings, so that means the entropy change for the surroundings is positive. But the entropy change for the system is negative. So these two are in conflict, and the only way that this is going to be spontaneous is if the entropy gained by the surroundings is more than the entropy lost by the system. So it's sometimes spontaneous. Next case, delta H is positive, so this is an endothermic reaction, and delta S is negative. So this means fewer microstates available. Okay, if delta H for the system is positive, it's endothermic, then that means energy flowed from the surroundings into the system. So for the surroundings, remember, S for the surroundings is going to be equal to Q for the surroundings over T. And since Q is going to be a negative number for the surroundings, that means the entropy change is going to be negative for the surroundings as well. Energy is less dispersed in the surroundings because of that. So that means that delta S for the surroundings is negative, and delta S for the system we already saw was negative. And so with both of these values that we're adding together being negative, they are not going to be greater than 0. So in this case, the reaction will not be spontaneous ever. Next case, delta H is positive and delta S is also positive. So this is an endothermic reaction, but one in which there's more microstates after the reaction. Energy is more dispersed. So we've already seen that if delta H is positive, then delta H for the surroundings has to be negative, which means the entropy change for the surroundings also has to be negative. So now we have conflict again. Delta S for the surroundings is negative, but delta S for the system is positive. So the only way that these are going to be resulting in a spontaneous reaction is if the entropy gained by the system is greater than the entropy lost by the surroundings. So this is another case where it's going to be sometimes spontaneous. So let's just summarize. delta H is less than 0 and delta S is greater than 0. Both of those driving forces for a reaction favor spontaneity, so this is always going to be spontaneous. If delta H is positive, that doesn't favor spontaneity, and if delta S is negative, that also doesn't favor spontaneity, and that's never going to be spontaneous. If the reaction is exothermic, that does favor spontaneity, but if it's a decrease in entropy, that doesn't favor spontaneity, so that means it's sometimes going to be spontaneous. And also, if it's an endothermic reaction where the entropy also increases, those are going to be sometimes spontaneous because the two driving forces, entropy change and enthalpy change, are in conflict with each other. So we need a tool for dealing with these sometimes situations. These are easy to evaluate, but we need to think a little bit more about these two cases. So let's develop a system-based tool for spontaneity decisions. And we're going to start out with this idea that the entropy change for either system or surroundings is going to be equal to the reversible energy change through heating divided by temperature change. Now, if you're following along with the follow-along notes that I gave you, if you're in my class, you're going to want to just put your pen down and watch for a while because the next thing that you're going to write in the notes isn't going to happen for a little bit. I'm going to do a little bit of development here. Because delta S is equal to Q over T, then that means delta S for the surroundings is equal to Q for the surroundings divided by T. But because Q for the surroundings is going to be the exact opposite of Q for the system, because the system and the surroundings make up the entire universe, that means delta S for the surroundings is negative of Q for the system divided by T. But Q for the system is delta H for the system, so the entropy change for the surroundings is equal to the negative of the enthalpy change for the system divided by T. So remember, the sum of the entropy change for the system and the entropy change for the surroundings has to be greater than 0 for this to be spontaneous. That's the entropy change for the whole universe. It has to be positive for every spontaneous event that occurs. If we know now that delta S surroundings is equal to minus delta H of the system over T, we can make a substitution here. So that means that the delta S for the universe is equal to the delta S for the system minus delta H for the system over T. And the advantage of what we're doing here is now we're turning this into a system-based tool because we don't have to worry about the surroundings anymore. We can just look at what's happening with the system. The next thing I'm going to do, which might seem a little bit counterintuitive, is I'm going to multiply through by negative T. So this equation then becomes negative T delta S for the universe is negative T delta S for the system plus delta H for the system. Then I'm going to rearrange a little bit. Negative T times delta S for the universe is equal to delta H for the system minus T times delta S for the system. So that's what I just came up with. Now let's think about what this means. Absolute temperature is always positive. So this is always going to be greater than 0. If the reaction is spontaneous, then delta S for the universe is also going to be positive. Two positive numbers multiplied by each other are going to be positive, so the opposite of that, the negative of that, is going to be negative. So if this reaction is spontaneous, then this sum on the right-hand side, delta H system minus T delta S system, will be a negative number. So if that sum is negative, the reaction is spontaneous. Conversely, if delta S universe is less than 0, then that means the reaction is not spontaneous. And so that means that that sum, delta H of system minus T delta S of system, will be a positive number. So we have this system-based tool. This quantity, this sum, is given the name change in free energy, or delta G. It used to be called, maybe it still is, Gibbs free energy change, and I think that's where the G comes from. J. Willard Gibbs was the person who outlined a lot of this. So that quantity is delta G. Now, because we're talking about delta G for a system, we can just drop the system markers, the subscripts there, and just use this as a definition of Gibbs free energy change or free energy change. So if you're following along on the notes from my class, this is the place where you pick up your pencil again, because we have our definition. Okay, so what's the meaning of this? If delta G is negative, then that's going to be a spontaneous reaction. If delta G is positive, that is not going to be a spontaneous reaction. And since there's a temperature term in here, we can see that spontaneity of some reactions is going to depend on what the temperature is. In terms of absolutes, G is H minus T times S, which is a little bit silly because enthalpy change and free energy change therefore can't completely fully be known, but that is the formal definition. Values of free energy change for formation are tabulated for lots of substances and can be used just like values of enthalpy change for formation, standard values. So standard values, both for enthalpy change and for free energy change. Remember, they're based on pressure is 1 atmosphere, 1 bar actually. Temperature is 298 kelvins, and concentrations are 1 molar, and it's for formation of 1 mole from elements in their standard states. So this thing that looks just like our Hess's law for enthalpies of formation can also be used to find free energy change for a reaction. They're reported in per mole quantities, intensive, so that means we have to adjust for moles, just like we did when using Hess's law. Let's do an example problem. Is CH3OH changing into carbon monoxide and hydrogen spontaneous at 25 degrees C? Remember, 25 degrees C is standard conditions, so we can use the values in this column to figure this out. So delta G naught, this is standard, for this reaction is going to be 1 mole times negative 137 kilojoules per mole minus 1 mole times negative 163 kilojoules per mole. That's for the CH3OH. And there is no formation value for hydrogen on the reactant part of this equation because it's an element in its standard state. Okay, so if you evaluate this, you come up with 26 kilojoules. So the answer to the question is no, it's not spontaneous because delta G is a positive value. This would have to be negative for this to be spontaneous. Another example problem. Is this spontaneous at 125 degrees C? 125 degrees C is not equal to the standard conditions. So that means we can't use these values. We're going to have to use the idea of free energy being equal to enthalpy change minus T times entropy change. So first let's figure out what is entropy change for this reaction, standard entropy change. Well, I'm going to have 1 mole of carbon monoxide, and its enthalpy of formation is negative 110.5 kilojoules per mole minus 1 mole of CH3OH times negative 201 kilojoules per mole for standard heat of formation. And when I sum those up, I get 90.5 kilojoules. Now let's figure out what delta S is, standard delta S. I have 1 mole times 198 joules per mole per Kelvin plus 2 moles times 240 joules per mole per Kelvin minus 1 mole times 240 joules per mole per Kelvin. Notice that these entropy values are always positive. They're negative. They're never negative. And the reason for that is because they are not entropy changes of formation. They are just entropies for that substance at that temperature. When we calculate this out, this could be a negative number. It's not in this case, 220 joules per Kelvin. Okay, so now we're going to take this value of delta S that we just calculated and the value of delta H that we just calculated, and we're going to put those in the free energy equation to find out what delta G is and make our spontaneity decision from that. So delta G naught is equal to delta H naught, that was 90.5 kilojoules, minus the temperature. Well, 125 degrees C is 398 kelvins, times entropy change. To make our units match, we're going to change 220 joules per Kelvin into 0.220 kilojoules per Kelvin. Kelvins are going to cancel. This answer will come out in kilojoules, and the sum is 2.94 kilojoules. So this is non-spontaneous because it's a positive value. Next question, is it spontaneous at 225 Celsius? 225 Celsius is 498 kelvins, so it's gone up from 398, it's another 110 degrees. Remember that delta H was 90.5 kilojoules, and delta S, standard delta S for this process, was 220 joules per Kelvin, or 0.22 kilojoules per Kelvin. Delta S and delta H are not going to change very much with increasing temperature or decreasing temperature. So we can use the standard values even if the temperature isn't the standard temperature. So delta G here is delta H, 90.5 kilojoules, minus temperature, which is now 498 kelvins, times delta S, which is 0.22 kilojoules per Kelvin. And this comes out to negative 19.1 kilojoules. Well, this is less than zero, so our decision is it is spontaneous because delta G is less than zero. We can see from those last few examples that temperature makes a difference for spontaneity. As the temperature got higher, we went from a non-spontaneous reaction to a spontaneous reaction. Let's look at that a little more generally. Let's take the case where the enthalpy change and the entropy change are both positive values. This is one of those we're not sure, it depends situations. One way to visualize this is by making a graph of free energy change and absolute temperature. Remember that delta G is equal to H minus T delta S. So if we're at absolute zero, T in this equation is zero, so that means the second term in this equation is zero. So delta G is just equal to, that should be a delta H. And that's a positive number. So that's the starting point for delta G, whatever value of delta H was. As the temperature gets bigger and bigger, remember that delta S is positive. So, and absolute temperature is always positive. So you're taking away a larger and larger positive value from a positive value. So that means it's constantly decreasing. So this graph would look like this. And at some point, the value of delta G transitions from being positive to being negative. At that point, at that temperature, and any temperature higher than that, the reaction is now spontaneous. Next case, if they're both negative. This was the other one of the we're not sure, it's not always certain if it's going to be spontaneous or not spontaneous. We can visualize the same way that we did before. If you're at absolute zero, then delta H and delta G are the same number, and it's negative in this case. But if delta S is negative, then T, which is always positive, and delta S is a negative number, you're subtracting a negative number that's getting bigger and bigger in magnitude from a negative number, which means it's becoming more and more positive. So once again, you have a transition. You cross that zero line at some point. Before that zero line, delta G was negative, which means spontaneous. After that point on the graph, the reaction becomes non-spontaneous. So this is only spontaneous at low temperatures, whereas in the other conditions, it was spontaneous at only high temperatures. Now you should know why this is true, but there's a little shortcut to help you memorize this. When both of the inequality signs point towards the left on a temperature scale, where it's spontaneous points towards the left too, so low temperatures. And we saw in the previous example that when both inequalities pointed towards the right, the spontaneity was on the right side of the temperature scale, so spontaneous at high temperatures. We can use this to make some interesting predictions like this one. What's the boiling point of water? Boiling point of water would occur when H2O liquid becomes H2O gas. What's delta G for that reaction? Delta G is delta H minus T delta S. Minus 242, I'm going to leave the units off here, kilojoules per mole, minus a minus 286 kilojoules per mole, and that comes out to a positive 44 kilojoules per mole. And delta S, standard delta S for this is going to be 189 joules per mole Kelvin minus 70 joules per mole Kelvin, which comes out to 119 joules per mole Kelvin. Now these are both positive values, so that means this is going to be spontaneous at high temperatures. So thinking about that graph again, here's temperature, absolute temperature, and here's delta G. We're starting out at positive. At some point, we transition to this becoming spontaneous after some temperature. What is that temperature? Well, we don't know, but we're going to figure that out. Because we know that when it becomes spontaneous, delta G has just crossed the zero line. So delta G is zero at that lowest possible spontaneous temperature. If delta G is zero, then we can use this equation with zero substituted in. So zero is delta H minus T delta S. So we're solving for temperature here. So that means T times delta S is delta H, which means that T is delta H over delta S. Keep forgetting my little standard symbols. Okay, so let's figure that out. T is equal to, our delta H here is 44 kilojoules per mole, and our delta S is, in kilojoules, 0.119 kilojoules per mole per Kelvin. Kilojoules per mole cancel out. We get 1 over kelvins. That's just kelvins. And when you do this calculation, you get 370 kelvins. Now, we only have two significant figures here, but that's pretty close to 100 degrees C, which is 373 kelvins. So this is a good prediction. One last topic for today, and that is coupling reactions. A non-spontaneous process can be coupled with a spontaneous process in a reaction where the two work together to make the overall reaction spontaneous. Here's an example. If you wanted to take copper 2 sulfide, which is present in lots of copper ores, and get pure copper out of it and separate the sulfur out, you couldn't do it spontaneously because delta G is a positive value, and that means it's not spontaneous. However, if you add oxygen to the mix, then this reaction will occur spontaneously. Any sulfur that would be produced would react with oxygen spontaneously to make SO2, and then if you sum this together, you can see that the sulfur is going to drop out, and you get Cu2S plus oxygen, making 2Cu, solid Cu, and SO2. And you were therefore able to isolate your copper, which was the whole point. Does this happen spontaneously? Well, yeah, because delta G is the sum of these two added together, and that's definitely going to be less than zero because negative 300.4 is way bigger magnitude than 86.2. Let's look at another example. How could adding oxygen make this spontaneous? Well, delta G for this reaction is negative 32.9 kilojoules per mole minus 2 moles times negative 51 kilojoules per mole, and that's a positive number, 69.1 kilojoules. So for this reaction by itself, it's not spontaneous. If we added oxygen, here's what could happen. That hydrogen that we created could react with oxygen and produce some H2O. Delta G for that process we can calculate from the little table that we have over here. These are elements in their standard state, so it's just going to be negative 229 kilojoules. So if we add these together, we have 2CH4 plus 1/2 O2 makes C2H6 and some water vapor. What's delta G for this reaction? Well, I'm not going to calculate it, but it's clearly going to be negative because negative 229 is a way higher magnitude than the positive number that we're adding together. So that makes this reaction spontaneous, whereas it wasn't before.